phase transitions. Now we're finally in the place to talk about what actually happens with the energy in the molecules when we change phases. So when we go from a solid to a liquid, we melt, right? Or a liquid up to a gas, we boil something. What's actually happening and what is the energy involved with those phase transitions? We're transitioning from one phase to the other. First, definitions. Let's talk about this. I draw this diagram here and I put solid on the bottom because I'm thinking in this diagram of energy as well. And if you think about energy going up here, in that sense, a solid has the lowest amount of energy. It's the coldest, it has the least amount of kinetic energy of the molecules. And then up slightly higher, I put liquid here, kind of in the next step up, because you got to warm things up to get them to melt and become a liquid, right? And so it has a little more kinetic energy. Those molecules are sliding past. Then if you give it a whole lot more energy, those molecules are really moving. You finally get up to the gas. So I kind of arranged it vertically. Now if I go from a solid to a liquid here, solid to a liquid, we call that melting. An ice cube melts to give you water. Or a liquid back down to a solid, yeah, we call that freezing. So we're very familiar with those transitions. Or if I start with a liquid now and go up to a gas, well, that would be boiling, or the more proper term, vaporization. Right? We're turning it into a vapor. So vaporization. And I see that I have my arrow backwards actually in this diagram. Let's go ahead and fix that. This one, where's my eraser? There's my eraser. Let's erase those guys and put it correctly. Vaporization is the liquid going up to the gas. If I go from the gas back down to the liquid, we call that condensation. So like on a hot summer day, you got a nice cold glass of water, ice water, and you get condensation forming on the outside, right? Now where did that water on the outside of the glass come from? Well, it came from the atmosphere. It came from the air, and it hit that cold surface of the glass, and it went from the gas phase to the liquid phase. Right? And so it's condensation. Now the third type here is you can actually go from a solid directly to a gas as well. Right? That's called sublimation. We don't see that, or we're not as familiar with that, right? But it certainly can occur. We can go directly and totally bypass the liquid phase, go directly from a solid to a gas, called sublimation. Carbon dioxide does that. You can go in most grocery stores, sell it as dry ice, they call it. Dry ice. You get a hunk of it and you take it out. It doesn't melt, or it actually evaporates directly, goes directly to the gas, and you get the smoke coming up of it. It's not really smoke, but anyway, that's sublimation, going directly. The reverse direction, going directly from a gas down to a solid, is called deposition. Deposition. And again, we do see that once in a while. On a cold winter's day, you might go out and have a bunch of frost on your windshield. Where did that frost come from? Well, there was vapor, water vapor in the air, hit that cold windshield, and it actually directly turned into an ice crystal. You got deposition occurring. So all of these phase transitions do occur just in normal life, and we got to call them by the correct name: sublimation, deposition, condensation, vaporization, melting, and freezing. So let's think about these one at a time here. If I go from the liquid to the gas phase, again, we call that boiling or vaporization or backward condensation. The first thing to note about that phase transition is that it's a dynamic equilibrium. That is to say, it's not like you just have one bulk of liquid that comes over and becomes a gas now. It's like, no, you've got molecules in each phase. I'm talking about during the phase transition itself. Okay? You got some that are liquid, you got some that are a gas, and they're going back and forth. Some of them here, some of them here. It's dynamic. It's not static. It's always back and forth, back and forth. Right? Now, you can talk about a relevant amount. Maybe 20% are as a liquid and 80% as a gas. And as they go back and forth, maybe there's a quicker transition from one to the other. And so that balance might change. Right? And that's what happens when you boil a liquid, actually. You start off with it all liquid and gas, and then you get this dynamic equilibrium that occurs, and eventually you end up with it all in the gas phase, because one direction is faster than the other direction. Right? But it's definitely dynamic. It goes back and forth. Do you have to get a liquid up to its boiling temperature for it to vaporize? The answer is no. Surprisingly, maybe, but it's no. I mean, if I spill water out, I got this puddle, and I leave it there for a couple days, do I come back and still find exactly that same puddle? No, I don't, because what happens? It evaporates. In other words, it turns to a vapor. It turns to a gas and then gets whisked away by the atmosphere, right? So that liquid has turned into a gas. It's vaporized, and yet it's just sitting there at room temperature. It's not boiling. It's not up at 100 degrees Celsius. It's probably down at room temperature, 20-ish or so. So you don't have to have it actually at the boiling temperature to get vaporization. you do have this tendency always for every liquid out there to turn into a vapor. Now, as you get hotter and hotter and hotter, it's got a greater and greater tendency to turn into a vapor. Okay? And so we'll have to define it and see how that actually happens. But that tendency to vaporize is what's called vapor pressure. The tendency to evaporate, if you will, vapor pressure. And if you were to set up a manometer, excuse me, where you got a bulb of liquid, and you got some mercury down here, and then you can see here it's starting to try to vaporize a little bit. Because it starts to vaporize, you're going to push that down, and you're going to get that height of the mercury there in millimeters of mercury. That would be a pressure. You can actually measure its tendency, and if it's got a greater tendency to turn into a vapor, it will push that up higher over here, and you'd have a greater vapor pressure. All right, so the tendency to evaporate is vapor pressure. It's literally a pressure, the pressure of that gas that has gone into the vapor state. Now, what would control the vapor pressure of a sample? Now, if I have, say, acetone versus water versus oil, do they all have the same vapor pressure? Well, no, because some of them evaporate very quickly. Acetone, you pour it out, you spill it, nail polish remover, right? Acetone, it evaporates very quickly. It's got a great tendency to vaporize and evaporate. In other words, it's got a very high vapor pressure. Where water, it'll evaporate, but it might take a couple days. Oil, you probably come back a month later and it's still there. Maybe a couple years you can get it dry out, something like a really thin oil like WD-40 or something. But yeah, it does not have a very high vapor pressure at all. So different molecules, different substances will have different vapor pressures. And so what controls that? You guessed it, van der Waals forces, intermolecular ones. We're going from a liquid where they're touching to a gas where they're totally apart. We're vaporizing it. Otherwise, we got to break all of those van der Waals type forces holding those together. So, for example, here, 10.5 from the textbook, we've got ethanol. We've seen that before. Ethylene glycol, which is, well, 2 carbons here. I don't know why I just do that by mistake, sorry. We've got 2 carbons with 2 OHs. Diethyl ether, 2 carbons, an O and 2 more carbons, and then water, of course, we know. Of course, ethanol, that's the alcohol in beer and wine. Ethylene glycol, that's what you find in antifreeze. Diethyl ether, puts you to sleep if you smell it too much, if you breathe it in. And then water, excuse me. Which one would have the highest vapor pressure? Which one would have the lowest vapor pressure? Well, again, we got to start thinking about what are the intermolecular forces. I'm looking through here, and 3 of these all have H bonds. Water has H bonds, this one is going to have H bonds, and this one's going to have H bonds. This is the only one that does not. It's got dipoles, but it does not have H bonds. So if I talk about the forces, let me add this, the intermolecular forces that are involved, this one has very low forces. They're not held very strongly together. The other 3 all have H bonds, and they are going to be held together. Now you think about this, water, pretty much it has H bonds. Right? Yeah, it's going to have London as well, sure, but there's not much surface area. There's not many. They're not big atoms, right? They're not big molecules, so there's not going to be a lot. Right? Ethylene glycol has those London ones because it's got a much larger one. It's got these 2 carbons here as well, and it's got 2 OH groups. You got 2 possibilities of H bonding there. Right? Ethanol looks like it's somewhere in the middle. It has 1 possibility, 1 OH, and it's got those Londons. Right? So if I'm thinking of increasing forces, I would say this one's next. So if this one's low, we'll call it number 1. Water would be number 2. This one would be number 3. And this one would be the highest because it has, again, a large amount of H bonding with those 2 OH groups, and it has a larger amount of dispersion forces compared to the smaller one like water. Okay, so there's the order of the forces, which means now I can think about vapor pressure. With vapor pressure, the stronger forces, like that, would have a smaller vapor pressure because they're not going to have a tendency to vaporize because they're being held together so darn tightly. Where something that's not being held tightly has just weak forces, they can pop off easier, and so they're going to tend to evaporate quicker, which means they have a higher vapor pressure. Right, so vapor pressure, this is the highest right there, the one with the least forces. This one's going to be the lowest. Right, so if we call this again 1, we'll put this number 4 at highest. We just put them in that same order as before. Okay, and so again, the highest one went with the lowest. This one will be next, number 3, counting down. This will be number 2, and then the lowest one there is with the strongest intermolecular forces. All right. Another thing that affects vapor pressure is temperature. And we've already mentioned this quickly before, as I increase the temperature, I give the things more kinetic energy. Those molecules having more kinetic energy, they move around, they tend to be able to break free of each other better. And so as I heat a liquid up, its vapor pressure is going to increase. Its vapor pressure goes up, and it goes up, and it goes up. And so, let's take some water at room temperature. Maybe it's got a vapor pressure of, 18, 20 torr, something like that. If I heat it up, now it goes higher. Now it's got 50 torr. If I get it up a little higher, maybe it's in the hundreds of torrs or whatever, something like that. If I can get it up high enough where it equals 760 torr, that is to say the same as the atmosphere, that will be the boiling point. See, you've got this liquid. It's trying to evaporate, and it's got a little vapor pressure. Again, maybe it's 17 torr, let's say. You got the atmosphere, it's pressing down on it with 760 torr, right? 1 atmosphere. And so, if you will, this liquid is being held down by the atmosphere. I heat it up. Now it's got a bigger vapor pressure. I heat it more. It's got even a bigger vapor pressure. Eventually, it will have the same pressure pushing up as the atmosphere is pressing down. Therefore, now it can compete. Now it will send all of its molecules essentially up into the vapor phase, and that's what we call boiling. So if you look at this chart here from the textbook, here's water, the blue curve here. Water starts down here, very low. This is pressure down here. So they're talking in kilopascals. Keep in mind, 1 atmosphere in kilopascals, well, there's 101.325 pascals in an atmosphere. So there's 101, write this down here, 101.325 kilopascals in 1 atmosphere. And so this dotted line right here that they've drawn is 1 atmosphere of pressure. Excuse me. So water at a cold temperature, way down here, 0, 20, 40, it doesn't have much vapor pressure. It doesn't have the kinetic energy. So very low on its vapor pressure. But as I heat it up, especially I get above 60, 80 here, it starts climbing quite a bit. Right? And eventually, when I hit 100 degrees Celsius, that water line has climbed high enough so it actually equals, the vapor pressure equals the atmospheric pressure. And it boils. That's what we call the boiling point. Right? 100 degrees, that's where it equals the atmospheric pressure. Hey, if you're up on a high altitude, maybe you live up in Denver or something like that, you're at a higher altitude, the atmospheric pressure is lower, which means it might be like down here, which means water, you don't have to even get it up to 100. Maybe you only get it up to 95 degrees and it boils. Right? The actual boiling point changes because you have a lower atmospheric pressure at those high altitudes. Different substances would have a different curve. Here's ethyl alcohol. Again, that's ethanol. That's what's in beer and wine and such. You get it up. Its actual vapor pressure goes up a little faster, and you have to only get it up to about 78, 79 degrees before it boils. Ethylene ether, or ethyl ether, excuse me, you only have to get it up to, looks like, about maybe 35 or so before it boils. Again, we're just talking about those intermolecular forces and how quickly can you overcome those forces to give a high vapor pressure. Ethylene glycol, with all of its double H bonds and its London dispersion that we talked about before, even at 80 degrees here, even at 140 degrees, very, very low vapor pressure. You have to heat that up a lot before it boils. Well, that's why we add it to the radiators and such in cars, because it's not going to boil away. It's going to stay as a liquid and still be able to act as a cooling media, whereas water, pure water, by that temperature would have boiled away and just turned to a gas. Engines run a lot hotter than 100 degrees Celsius after all. Okay, now that we got the idea of vapor pressure, let's think about the energy considerations of vaporization. Here, example, you got water as a liquid, it boils, turns to water as a gas. That is a simple chemical reaction. It's just going from the liquid state to the gas state, and as such, I can talk about the delta H, the change in enthalpy of that reaction. Of course, this is a vaporization reaction, right? It's going from liquid to gas, so they call it delta H VAP, vaporization. For water, 44.01 kilojoules per mole. So it actually, you have to increase its energy by that much to get it to turn to a gas. Makes sense. Every material out there is going to have a different delta H of vaporization, and you'd have to go look that up in a table if you want to know what its values are. What about the reverse way? What if I go from a gas, so going backwards, right? If I go from a gas to a liquid, what does that look like? Well, here it's going to give off that energy, but it's the same reaction. It's just been flipped. And if you remember Hess's law, if you change a reaction, all you do is change the sign of delta H. And so if from a liquid to a gas, that's positive 44, then from a gas back down to a liquid, negative 44. Pretty simple. Think about this too. Liquid to a gas, you have to give that liquid energy. In other words, if you are the liquid, you're really absorbing a lot of energy in order to turn to a gas. We would call that an endothermic reaction. Endothermic reactions have a positive delta H. Whereas if I'm going from a gas to a liquid, gas, very high energy, it gives off that energy to go down to a liquid. It's releasing that energy. That's exothermic. And so a negative delta H makes perfect sense. That's essentially what happens, by the way, in perspiration. You sweat because your body's trying to cool itself, so you get that water on your skin. The water can evaporate off your skin. As it evaporates, you're turning from a liquid to a gas. That takes 44.01 kilojoules per mole energy. Where does it get that energy from? Your skin. So it's actually sucking that energy out of you, which is a cooling. Right? So it makes perfect sense. The Clausius-Clapeyron equation relates what is the vapor pressure of those type of transitions then to temperature. We talked about, again, as you increase the temperature, the vapor pressure also increases. The equation that relates those two involves the delta H of vaporization that we just talked about, and here it is. The Clausius-Clapeyron says that the vapor pressure equals some constant A, whatever that is, times E, the natural log base, E to the negative delta H over RT. Right, so A is just some constant. Again, delta H, enthalpy of vaporization. R is the ideal gas law constant. Make sure you use the right one, though. Don't use the one with liters and atmospheres. We want the ones in the standard SI units, which would be joules per mole Kelvin. 8.31451. Got to use that one. Don't use the other, okay? All right, so 8.31451. This constant A will change from chemical to chemical, and so if you'd have to look that up. But more importantly than looking it up, look at the form of this equation. If I just did a simple rearrangement of it, I'm going to squeeze it in right here. P equals AE to the negative delta H over RT. If I take the natural log of both sides, the natural log of P equals the natural log of that whole big thing. AE to the negative delta H vaporization over RT. Right. If you are multiplying on the inside of the log, that's the same thing as adding on the outside of the log. Remember your rules of logs. So that's the same thing as the log of A plus the log of E to the negative delta H. So in other words, I'm taking the log of the exponential. Those just cancel each other, and you get a negative delta H of vaporization over RT, right, which is what I have here. The natural log of A, so it's a pretty simple manipulation, right? The natural log of the natural log of vapor pressure equals the log of A minus delta H of RT. Take that and just rearrange it a little bit, and I mean very little. Just swap the terms, the order. Natural log equals negative delta H over RT over R. I separated the 1 over T over here, plus the log of A. Again, I just took those and reversed the order. To put that in a standard form of a straight line. The Clausius-Clapeyron equation is actually linear, as long as you take the log of P. That's your Y. Here's your X. So here's mx plus B, right? Here's your X is 1 over T, the reciprocal of temperature. Your slope is going to be negative delta H over R, and your y-intercept will be log of A. Hey, that's pretty interesting because you can actually measure then the delta H of vaporization of any liquid, of anything you have, by measuring its vapor pressure at different temperatures. If I did that, so I'd have temperature 1, temperature 2, temperature 3, and I'd have the vapor pressure 1, vapor pressure 2, vapor pressure 3. That'd be pretty easy to do. Just set up a manometer and measure that height of that mercury, right? At different temperatures, just increase it. Plot those out. I should get what should be a straight line. You know, you have the dots on it here. It won't be perfect, but you could fit a straight line to it. That might be my data like that. I could fit a straight line, and the slope of that straight line, according to up to here, the slope would equal negative delta H over R. Negative delta H over R is the slope. All right, so I can get my straight line. I can measure the slope. I know what R is, 8.31451. Plug those in, and I've got my delta H of vaporization. Very easy to actually measure and record. Now there's another way that the Clausius-Clapeyron equation shows up, and that's by just comparing discretely two different temperatures and vapor pressures. So call it T1 with P1, T2 with P2. So here it is. I just took the Clausius-Clapeyron equation with P1 and T1 filled in. Here's P2 and T2. And add those two together. Maybe that's the easiest way. Or if you want, you could solve them both for log A and set them equal to each other. It works out to be the same, however you want to think about it. And so if I've got these two, and that's what I did here, solve this top one for log of A. So I'd have log of, I worked with the bottom one first. Log of P2 would equal, log of P2 plus delta H, just move it over to the other side there, would equal log of A. And this top one, log of P1 plus delta H with the T1 equal log of A. So they both equal log of A, so they equal each other. So there you go, I've got them equal to each other. If you're subtracting on the outside of a log, that's the same as dividing on the inside. And so that's what I did over here with the P2 and the P1. That's the log of P2 divided by P1. And here, I just took this and sucked out a delta H of vaporization over R. And so I've got that, a negative version of it, and I've got 1 over T2 minus 1 over T1. Here is an alternate form then of the Clausius-Clapeyron equation, one that you very often see. Well, you just have two different temperatures, two different pressures. You can put them in and solve for delta H again. Or you could also use it to predict, I guess, temperature 2 when you know P2 and P1 and T1, and you also know delta H. Whatever you do know, plug it in, solve for what you don't know. Right, so let's try an example of that here. Example 10 says you have isooctane. And they did exactly what we just said. They measured the vapor pressure at 34 degrees, turned out to be 10 kilopascals, and at 98.8 degrees, turned out to be 100 kilopascals. They say, hey, what is the delta H of vaporization? Well, I can use the Clausius-Clapeyron equation to do that. I always have, again, the log of P2 divided by P1 equals negative delta H of vaporization over R times 1 over T2 minus 1 over T1. You've got to put it in Kelvin, just like with the gas laws. Right? The pressures, because you're taking a ratio, the units are going to cancel. So as long as you use the same units, consistent units, it doesn't matter what they are. Okay. And so let's try this. Log of P2, which is 100 kilopascals over 10 kilopascals, same units, so I'm good, would equal negative delta H of vaporization over R. R is 8.31451 joules per mole Kelvin. Okay. Times 1 over T2, put it in Kelvin, so T2 is 98.8, which turns out to be 372.0 Kelvin, minus 1 over 307.2 Kelvin, right, converted to Kelvin. Now I go over to my calculator and I plug this all in and hopefully get the right answer here. So let's see, what is the log of 10 over 1? So that's the log of 10. So if I said, what is the log of 10 on the left side there? So that equals 2.3026. Over here I've got negative delta H over 8.31451. And then in here I've got 1 over 372 minus 1 over 307. Was that 307.7.2? 307.2. Oops, I wasn't typing in my calculator. Let's try that again. Sorry. 1 over 372 minus 1 over 307.2. So that whole thing equals, that came in that way for me. That's funny. That's okay. Negative 567.0 times 10 to the minus 6. All right. So now finally I can, let me give myself some more room here. All right. I can solve for delta H. Delta H would equal, go over my calculator this time so I don't forget that, 2.3026 times a negative 8.31451 equals that, divided by a negative 567 e minus 6 equals, and it didn't do it for me. Let's try that one more time. Negative 9, no, I could just use the answer. That answer divided by negative 567 e minus 6 Sorry, I'm kind of working crossways on my keyboard there to try to get this answer. All right, I'm getting delta H is 33.7 times 10 to the third. And that would be joules per mole, or in other words, 33.7 kilojoules per mole. There's the delta H of vaporization of isooctane. All right. Let's do one more example here of the energy involved with a phase transition. Example 10.9. Perspiration cools the body. Yep, we talked about that. How much heat is removed from the body? So they're asking me for joules, right, for heat. When 1.5 liters of perspiration water evaporates at 37 degrees Celsius. Why did they use that temperature? Well, that's body temperature. Right? And so 37 degrees Celsius. Delta H of vaporization at 37 is 43.46 kilojoules per mole. All right, so how do I do that problem? Well, I'm starting with 1.5 liters. 1.5 liters of water. Okay. And I've got the fact that it absorbs 43.46 kilojoules for every mole. Well, I've got liters. So the first thing is to convert this to moles. That's how I can do, because liters to milliliters, there's 1,000 milliliters in a liter. Liters are gone. And you remember the density of water is exactly 1 gram per milliliter, or close enough. So I actually got grams, and then I can convert from grams to moles. So all that stuff that we've done before. 1 mole is roughly 18.01 grams for water. All right, now that I got moles, I can use my delta H, which says, hey, I get 43.46 kilojoules for every mole that evaporates. My moles cancel, and there we go. I'm left with energy. So I go to my calculator and type this all in. 1.5 times 1,000 times 1, don't need to enter that in, right? Divided by 18.01, and then times 43.41 equals 3.6 times 10 to the third. So that's times 10 to the third kilojoules. In other words, that's 3,600 kilojoules of heat are actually absorbed. All right. So the energy associated with the transitions of liquid going to gas, which includes vapor pressure, the Clausius-Clapeyron equation. Those are the type of calculations we can do with those type of transitions. Next, we're going to be a little easier. The energy transition, for example, of a solid going to a liquid. Well, we call that melting and freezing. Right? That delta H is called fusion. Fusion. All right, so fusing those liquid molecules together to give you solid, I guess, right? So, of course, in the one direction it's endothermic, and the other one it's exothermic, just like what we saw with vaporization. So if I'm going from the solid to a liquid, that would be endothermic. You're absorbing that energy. Or liquid going back to a solid, that would be exothermic because you are releasing it. And again, you can look up what those values are, what delta H is, and they're just going to be the opposite of each other. Right? Or a solid to a gas, that's sublimation, deposition. They would call that delta H, or the change in enthalpy of sublimation. Now, one last thing here to think about. If you've got, oh, sorry, I was just looking ahead there. If you have this kind of a diagram where we're showing the energy involved with going from a solid to a liquid and then a liquid to a gas, you can see that this has delta H of fusion. This would be delta H of vaporization. If I went all the way, that would be this arrow plus this arrow, which equals the delta H of sublimation. So these guys are always going to be related by this guy right there, the fact that the delta H of fusion plus the delta H of vaporization equals delta H of sublimation. Finally, now that we know and understand the energy involved with these transitions, we can talk about heating and cooling curves. Here is a heating and cooling curve of water. Look on the x-axis. We've got the amount of heat added. So we're starting and we're just putting a flame on this or something. We're just heating it up. We're adding all this energy, all this heat to it. And we got a temperature stuck there in our sample, so we're measuring the temperature of it. Now we're starting, it looks like, way down here at -10. Well, that's going to be ice, right? -10 degrees. And so that's solid. And as I add heat, what happens? The temperature goes up and up, makes sense. And it's going to keep on going up until it reaches 0 degrees. where it melts, right? And so this first little step right here, you've got solid ice during the whole part of it, and it's just getting hotter and hotter. The temperature's going up on it. Right? Then, during the melting process, the temperature stays the same. You see, in the first part, as I was adding the heat, that heat went to making those molecules move faster, which went to, of course, a higher temperature. But here, when we're doing the phase transitions, that heat that I'm adding is not going to a temperature increase, it's going to a phase change. We're actually getting those solid ones to finally break those and turn into liquid so they can slide past each other. So I can add a lot of heat. I'm going left. I'm just going from the left to the right, to the right, to the right, to the right, going across here. But all that heat is going to the phase transitions. Therefore, the temperature stays constant. It's going to stay right at 0 degrees. And it's going to stay there until all of that water has finally melted to a liquid, all that ice to a liquid. Once it's all finally melted, now it's a liquid, and I keep adding more heat. What happens? Now I've got the temperature of that liquid going up. It's getting hotter liquid, because I'm not doing a phase transition anymore. Now it's just those molecules are given more and more kinetic energy. So it gets hotter. During this whole big thing, it's all liquid. It's just getting higher and higher temperature, hotter and hotter liquid, until it finally gets up to 100 degrees. And we know what happens there. Then the liquid of water starts to boil off and turn into steam, turns to vaporization. And so now as I go from the left to the right, I've got, again, a flat line where that additional energy is being used to do the phase transitions to a gas at delta at 100 degrees. And it's going to stay at 100 degrees until, again, all of it has turned into the gas. And then if I keep adding more energy at that point, well, now I've got the gas water going hotter and hotter and hotter, and it's just going to keep climbing up there. So, key kind of a consideration on a heating and cooling curve. Number one, right, you're going to go to hotter temperatures, that's for sure. Right? But number one, you've got two different types of regions. The first type is where you've got just some kind of a material and it's getting hotter. That's like in this first part of the curve, or the second part of the curve here, or this third part of the curve. We're actually climbing up with temperature. Right? The second type or second region type here are the flat areas. That's where the phase transitions are occurring. The temperature does not change, so it stays flat down there. And here we're going from a solid to a liquid, or here we're going from a liquid to a gas. Two different types of regions. And I can talk about, well, what is the energy that each region is going to suck up. Right? The steepness of these depends on the heat capacities. How much heat do they absorb to cause 1 degree change in temperature? Those are going to be the slopes, if you will, of those regions. The flat regions, they're controlled by, well, how much energy does it take to make the phase transitions? If you look at this, this is a fairly well done figure where I've got a fairly small, let us say left to right, it's not very wide, transition here from a solid to a liquid, but look how long this one is from a gas to a liquid. In other words, if I start right here, go back to the x-axis, this amount of heat all the way up to this amount of heat, so that total energy from there to there is how much total energy it took to make that liquid into a gas. Keep in mind, those gas molecules have a lot of energy, and I'm literally completely ripping those liquid molecules apart and giving them enough kinetic energy to be a gas and remain a gas. That takes a lot of energy. Gases are very, very high energy compared to liquids. To go from a solid to a liquid, yeah, it takes energy, but not nearly the amount. Look how short that line is compared to the liquid to gas transition. Okay, can I calculate the amount of energy in each transition? Sure. We've already done this kind of calculation before. If you've got a substance and we're going from one temperature to another, then the heat involved there, use green, the heat involved there equals just the mass times the heat capacity times the change in temperature, mc delta T. Now keep in mind that while like in this cooling curve or this heating curve here, while the mass of the liquid or ice or gas, the mass of the water, let's say, remains constant, it's just the phase that are changing. We're not adding more liquid in, or we're not removing it. The total amount of liquid, or water in this case, stays constant, which will be m in this equation right there. The heat capacity is going to be different. The heat capacity, the value for it for water, the liquid, is a different value than it is for water as a gas or water as a solid, ice. And so depending on what part of the curve you're in, you need to use a different value for C. And you're going to have to look those values up. Of course, the change in temperature is just, from this first part, it looks like it started at negative 10 and then went up to 0. Here, the second part, it started at 0 and it went up to 100. Right? Third part, it started at 100, it went up to, looks like 120 maybe, something like that, 110. I don't know, hard to tell for sure there. Okay, so the change in temperature is going to correspond to what part of the curve that you're in as well. Now, what about the phase change? Well, we talked about the enthalpies of vaporization and the enthalpy of fusion. Those tell you how many kilojoules of energy per mole. Well, if I just multiply those by the number of moles, then I'll have the total amount of energy of the phase change. And so that's what I got here. The heat involved with the phase change is just how many moles do I have times the delta H of that phase change, which again I can look up in some table. Alright, so example 1010. This is going to be a long example, but we'll get through it. It says how much heat is required to convert 135 grams of ice. So there's my mass, right? 135 grams of it at negative 15 Celsius. So it starts pretty cold, way down there. And we're going to heat it up, and we want to convert it all the way to steam. So we're going to start with solid, then we're going to melt it, then we're going to go to a gas. We're going to vaporize it to steam at 120 degrees. So that's where we're finally going to end. They want the total amount of heat that's required for that. So if I was to draw that curve out, right, here's my heat down here, Q. Here's my temperature. I'm going to start right down here, let's say, where I've got negative 15 degrees Celsius. It's going to warm up until it finally hits 0. That's when it's going to start to melt. It'll stay at 0 until it's all melted. So over here, solid. Here I've got the phase transition, and then it's going to start to heat up again as a liquid because it's all melted. And it's going to keep on heating up and heating up as I add that energy until I finally get to 100 degrees where it's going to boil. Here it's going to do the phase change until it's all boiled finally, and then now I've got gas. So here's the gas phase, and it's going to go up, and it's finally going to end at 120 degrees Celsius. So there's my curve. Here's going from a solid to a liquid. Here's going from a liquid to a gas. Those are my phase changes, and solid, liquid, gas on the individual portions of the sloped parts. So what is the total amount of heat? I see 5 different regions. We can call, whoops, hit the wrong thing. We can call this Q1 when it's a solid, Q2 when it's actually melting, Q3 is when it's a liquid, Q4 here where it's changing from a liquid to a gas, so it's boiling, it's vaporizing, and finally, well, I'm going to put it up here, Q5 when it's a gas and heating up. So the grand total, I would just add those guys up together. My total heat is going to be just Q1 plus Q2 plus Q3 Q4 and Q5. Add them all up. That'll give me the total amount of heat that's required to do this. I'm going to have to look some things up here and calculate it. They told me I have, how much did I have? 135 grams of water. Of course, if I convert that to moles, I'm going to need to do that anyway. Grams to moles, 1 mole is 18.01. And so that equals, let's go over to the calculator here, 135 grams. Oops, there we go. 135 grams divided by 18.01. And so that's the same thing as 7.496 moles of water. So I've got that many grams, I've got that many moles. That's going to be useful to know. All right. Let's think about each one of these. Q1. Q1 is when it's a solid. The heat involved with a solid is going to be equal mass times its specific heat times its change in temperature. For this case, I've got 135 grams. That's its mass. What's its heat capacity? I know the heat capacity of liquid water is 4.184. But what is it of solid water, of ice? Well, we're going to have to look that up. And so if you go over here to your textbook, let me pull this over here. If you go to the appendices in the back, here's properties of water right here. Okay, so let's look through these. Got the density, it's a function of vapor pressure. Hey, we've used that before, right? Vapor pressure again. These we're going to have to talk about in a later chapter. pKw. No, here we go. Specific heat capacities. And so I've got for liquid water, like I said, I know that, 4.184 joules per gram per degree Celsius. I've got for solid water, ice in other words, 1864 joules per Kelvin per kilogram. give us a strange units. Like, thanks a lot, right? And then here for gas water, for vapor water in the gas state, 2093 joules per Kelvin per kilogram again. Right. Well, how many kilograms do I have? If I have 135 grams, I guess that's 0.135 kilograms. So I can do that. All right. All right, so let's go back to my notes here. Instead of grams, let's just go ahead and use kilograms, since that's what they're giving us. Or I convert the other ones to per gram, but I think this would be easier. This is the same thing as 0.135 kilograms, and so that's what I'll use, 0.135 kilograms. Again, the C, and I did the math, now I'm doing C, the specific heat for, this is for ice, right, Q1, when it's a solid. For the solid is 1864 joules per Kelvin kilogram. All right, 1864 joules per Kelvin kilogram. So my kilograms cancel. And now the delta T part. Delta T, let's see, it started at negative 15, then it went up to 0 where it started to melt. So 0 minus a negative 15. It's always final minus initial, right? All right, let's put that through on the calculator and see what that first part is anyway. I've got 0.135 times 1864 times 0 minus 15, that's going to be 15, equals. All right, so 3,775. Everything cancels here except for joules. So that many joules. That's for just Q1. All right, let's go to Q2. Q2, now I'm in my actual phase change, right? Q2, from the solid to a liquid. The amount of heat for a phase change is equal to the moles times the delta H. Which delta H is this? This is for melting between a solid and liquid. That's the delta H of fusion. Remember, vaporization is between liquid and gas. Fusion is between solid and a liquid. Okay, what numbers do I have there? I already figured out the moles. It was 7.496 moles of water. I need delta H of fusion next. I'll go back to that appendix here. Right below here, here's my standard melting temperature and their enthalpies of the transition. So that's exactly what I need. Delta H in terms of kilojoules per mole, right, of either melting or boiling. I'm talking about melting, right? And so 6.088 kilojoules per mole. All right, I already forgot what it was. 6.088. Okay, 6.088 kilojoules per mole. Up here I got joules. Here I got kilojoules. Well, this is a large number, so I'm going to go ahead and convert that up here. That's 3.775 kilojoules. That way it'll all come out in kilojoules. For Q2, that's pretty simple. Just multiply those two numbers together. 7.496 times 6.088. All right, 45.6. 45.64 actually. Kilojoules per, not just kilojoules, sorry, not per mole, just kilojoules. Let me rewrite that a little clearer. Hey, look at that difference. To heat up the ice from negative 15 to 0, it only took 3.7 kilojoules. To get the transition to occur, 45. A lot more heat was required to do that. All right, keep going. Q3. Now in Q3 up here, now I'm in the liquid state. And so I've got not a phase transition, but just a material getting hotter. So we're back to this equation again, MC delta T. The mass, it's still 0.135. I'm not adding any or removing any, so 0.135 kilograms. Now I need C, the heat capacity of liquid water. All right. Again, over here, we got that. It's 4,184 joules per kilogram per degree Kelvin. Right here, 4,100. The 4.184 would be per gram, which is kind of what we're more used to, but we're working in terms of kilograms. So 4,184. 184. Again, that's joules per Kelvin per kilogram. My kilograms cancel. And then my delta T, well, my final is going to be 100 degrees. I start with 0. There's my delta T for this part of the curve. Okay, go to the calculator and punch this in. 0.135 times 4,184 times 100. 56.48. 56.48. And it's times 10 to the third, so that's kilojoules, right? Because here we had joules, 10 to the third means kilojoules. So that's how much heat it took for the third part. It took even more to heat that water up than it did to melt it, apparently, right? Because it took it 45.6 to melt, but it takes 56.48 to bring it up to 100 degrees. Q4. Now we're going to, at Q4, we'll go over here. Now we're doing the phase transitions from the liquid to a gas. Again, that takes a lot of energy. I would expect this to probably end up being the largest number. Let's find out. We're back to a phase transition, so it's N times the delta H, this time of vaporization, because we're going from a liquid to a gas. N we know is 7.496 moles, as before. I need to look up delta H of vaporization. Go back to the appendix here. Here it is for boiling, for vaporization. It's 40.656 kilojoules per mole. 40.656 kilojoules per mole. All right, so moles will be canceling. I'll be left with kilojoules. Let's go to the calculator and try that. 7.496 times 40.656. 300, oh yeah, look at that, it's big, right? 304.8 kilojoules. Yep, like I said, that's the biggest one yet. It takes a lot of energy to get something to turn to a gas. We're almost done. We have just now Q5 to talk about. In Q5, you scroll up here, Q5 is the part where we've got just the gas getting hotter. So we're back to this equation again, mc delta T, but this time it's for the gas water. Mass is still 0.135 kilograms. All right. What is the heat capacity for steam? What is C for steam? So I go up here. Here's the gas form. 2093 joules per Kelvin per kilogram. 2093 joules per Kelvin per kilogram. So kilograms cancel. Now I've got to get the delta T, the third part there. And they told me I end this at 120, right? That's where we're finally bringing it up to. So this last leg was final temperature of 120 minus 100, so that's 20 degrees on that final one. All right, calculator, 0.135 times 2093 times 20 equals 5.65, again joules, so that would be kilojoules. So we're talking about 5.651 kilojoules of my last leg. All right, there we go. There's Q1 through Q5. The grand total then, I would add it all up. Let's try that on the calculator. 3.775 plus 45.64 plus 56.48. Hope I don't make a mistake here. Plus 304.8 plus 5.651. 651. There we go. Well, if I've done it correctly, it is 416.3 kilojoules. So that's a lot of heat. But that's how much total energy it took to get that water. And I think probably if we go back to the textbook, we can make sure we did that correctly. Let's just check ourselves here for phase transitions. All the way down near the bottom here. There we go. We're going to go 135 grams again from negative 15 to 120, blah, blah, blah. Hey, there you go. 416 kilojoules, exactly what we got. So it's a long calculation, but it's just broken up. It's really 5 problems, right? Because you got the solid, and then the phase transition, then the liquid, then the phase transition, then the gas. Add them all up together, and you get your grand total.